Welcome to Math, Week 11, Solving Quadratic Equations. This is Module Math 1 on the Math Tutor Self-Study track. Today we cover 4 methods for solving quadratics, the discriminant, and where the quadratic formula actually comes from. There is a 10-question practice quiz at the end, so stick around for that. A quick thank you to our sponsor, subthesis.com. If you want to level up your math skills with structured, self-paced courses, check them out. Link is in the description. Now, back to the lesson. Here is what we will cover today. We start with 4 solving methods: the square root property, factoring with the zero product property, completing the square, and the quadratic formula. Then we look at how the formula is derived from completing the square. After that, the discriminant and complex roots. We connect it all to machine learning with stationary points, and we finish with a 10-question practice quiz. A lot to cover, so let us get right into it. Method 1. The square root property. Use this when the equation is already in the form x squared equals some number. The idea is simple. If x squared equals k, then x equals plus or minus the square root of k. The plus or minus is critical. You must report both the positive and negative roots. Let us look at 2 examples. First, x squared equals 25. Taking the square root of both sides gives x equals plus or minus 5. Second, x squared equals 7. Here x equals plus or minus the square root of 7, which is an irrational number, and we leave it in exact form. A common mistake is dropping the plus or minus and only reporting the positive root. That gives you half the answer. Method 2. Factoring with the zero product property. Use this when the quadratic factors neatly into 2 binomials. The zero product property says, if the product of 2 factors equals 0, then at least one of the factors must be 0. Let us work through x squared minus 5x plus 6 equals 0. We factor the left side into x minus 2 times x minus 3 equals 0. Setting each factor to 0 gives x equals 2 and x equals 3. The critical thing to remember is that the zero product property only works when one side is 0. If you have a product equal to 12, you cannot set each factor to 12. The most common mistake is flipping signs. When you see x minus 2 equals 0, the root is x equals positive 2, not negative 2. Method 3. Completing the square. Use this when the leading coefficient is 1 and the middle coefficient is even. The steps are: move the constant to the right side, take half the middle coefficient and square it, add that value to both sides, factor the left as a perfect square, and take the square root of both sides. Let us go through it step by step. Start with x squared plus 6x plus 2 equals 0. Move the 2 to get x squared plus 6x equals negative 2. Half of 6 is 3, and 3 squared is 9. Add 9 to both sides to get x squared plus 6x plus 9 equals 7. The left factors as x plus 3 all squared equals 7. Take the square root. X plus 3 equals plus or minus the square root of 7. So x equals negative 3 plus or minus the square root of 7. The big idea is that completing the square is exactly how the quadratic formula is derived. If you understand this method, the formula is not something you memorize blindly. Common mistake: forgetting to add the squared value to both sides. If you only add it on the left, the equation is no longer balanced. Method 4. The quadratic formula. This is the universal method. It works for every quadratic equation, no matter how messy the coefficients are. The formula is x equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. For any equation in the form ax squared plus bx plus c equals 0, just identify a, b, and c and plug them in. Let us work through 2x squared plus 3x minus 2 equals 0. Here, a equals 2, b equals 3, c equals negative 2. Plugging in, x equals negative 3 plus or minus the square root of 9 plus 16 divided by 4. That simplifies to negative 3 plus or minus 5 over 4. So x equals 1/2 or x equals negative 2. Always simplify your radicals at the end. A common mistake is writing b squared as 2 times b instead of squaring the full value. When b is negative, you must square the entire negative number, which gives a positive result. Now that we have all 4 methods, how do you decide which one to use? Here is a simple decision flowchart. First question, is the equation already in the form x squared equals some number? If yes, use the square root property. It is the fastest. Second question, can you spot integer factors quickly? If you can factor the expression in under 30 seconds, go ahead and use factoring with the zero product property. Third question, is the leading coefficient 1 and the middle coefficient even? If yes, completing the square will be clean and efficient. And if none of those conditions are met, or you are unsure, default to the quadratic formula. It always works. The bottom line is that the quadratic formula is your reliable fallback for every case, but the other methods are faster when their conditions are satisfied. 8. Let us do a second worked example with a harder problem. Solve 3x squared plus 2x minus 4 equals 0. This does not factor neatly, and the leading coefficient is not 1, so the quadratic formula is our best bet. Identify the coefficients. A equals 3, b equals 2, c equals negative 4. Compute the discriminant first. B squared minus 4ac equals 4 minus negative 48, which is 4 plus 48 equals 52. Since 52 is positive, we get 2 distinct real roots. Now plug into the formula. X equals negative 2 plus or minus the square root of 52 divided by 6. Simplify the radical. The square root of 52 equals 2 times the square root of 13. So x equals negative 2 plus or minus 2 root 13 all over 6. Factor out a 2 from the numerator. X equals negative 1 plus or minus root 13 divided by 3. That is the exact answer. We chose the quadratic formula here because factoring was not practical with these coefficients. 9. Where does the quadratic formula come from? It is actually just completing the square performed on the general equation and then saved as a recipe. Start with ax squared plus bx plus c equals 0. Divide everything by a. Move the constant to the right side. Take half the coefficient of x, which is b over 2a, and square it to get b squared over 4a squared. Add that to both sides. The left side becomes a perfect square, x plus b over 2a all squared. Combine the right side over a common denominator. Take the square root of both sides, remembering the plus or minus. Isolate x, and you arrive at the quadratic formula. This derivation is worth understanding because it shows the formula is not magic. It is completing the square done once for all quadratics. The discriminant is the expression under the square root in the quadratic formula, b squared minus 4ac. We often call it delta. Its sign tells you how many real roots to expect before you even solve. If the discriminant is positive, the square root is a real number, and the plus or minus gives you 2 distinct real roots. The parabola crosses the x-axis at 2 points. If the discriminant equals 0, the square root vanishes, and you get exactly one repeated root. The parabola just touches the x-axis. If the discriminant is negative, the square root of a negative number is not real, so there are no real solutions. The parabola never crosses the x-axis. The roots become complex numbers, which we cover next. A bonus fact: the discriminant also appears in the distance formula and in determining the nature of conic sections. What happens when the discriminant is negative? We enter the world of complex roots. Take x squared plus 4 equals 0. Subtract 4, x squared equals negative 4. Taking the square root gives x equals plus or minus the square root of negative 4. We define I as the square root of negative 1, so x equals plus or minus 2i. These roots are purely imaginary. On the Argand plane, also called the complex plane, real numbers sit on the horizontal axis, and imaginary numbers sit on the vertical axis. So 2i and negative 2i are plotted as points straight up and straight down on the vertical axis. A common mistake is writing the square root of negative 4 as negative 2. Remember, you cannot just move the negative sign outside the radical without introducing I. In machine learning, complex eigenvalues show up in stability analysis, recurrent networks, and signal processing. Let us connect quadratics to machine learning. In optimization, we find stationary points by setting the derivative equal to 0, which often gives us a quadratic to solve. For convex loss functions, like mean squared error with a single weight, the loss surface is bowl-shaped. There is one minimum, and gradient descent rolls right down to it. Every stationary point is a global minimum. But for non-convex loss functions, which appear in deep learning, the surface has hills and valleys. Multiple stationary points exist, including local minima, saddle points, and the global minimum. Gradient descent can get stuck in a local minimum and never find the global best. This is why initialization and learning rate matter so much. The quadratic discriminant tells you whether the stationary points exist and whether they are real or complex. Complex stationary points mean the loss function has no real critical points in that region. Here is a deeper look at how quadratics connect to machine learning code. Imagine a function called Solve Quadratic that takes coefficients a, b, and c. First, check if a equals 0, because then it is not actually a quadratic. Next, compute the discriminant, b squared minus 4 times a times c. If the discriminant is negative, return no real solutions or handle it with complex arithmetic. If the discriminant is 0, there is exactly one root, negative b divided by 2a. Otherwise, compute the square root of the discriminant and return both roots. This kind of discriminant guard is essential in production code. Without it, taking the square root of a negative number throws a runtime error or returns not a number, which silently corrupts downstream computations. In gradient-based optimization, this same logic determines whether critical points are real, which directly affects whether the optimizer can converge. 14. Before we jump into the quiz, let us review the 5 most common mistakes students make with quadratics. Number 1. Dropped plus or minus. When you take a square root, you must write plus or minus. Forgetting it means you lose half your solutions. Number 2. Sign flip errors. When factoring, if you have x minus 3 equals 0, the root is x equals positive 3, not negative 3. Number 3. B squared versus b times 2. In the quadratic formula, you must square the entire value of b. If b equals negative 5, then b squared is 25, not negative 10. Number 4. Unsimplified radicals. Always simplify your square roots. The square root of 50 should be written as 5 times the square root of 2, not left as root 50. Number 5. Wrong method choice. Do not force factoring on a quadratic that does not factor neatly. If you spend more than 30 seconds looking for factors, switch to the quadratic formula. A professional tip. After finding your solutions, substitute them back into the original equation to verify. It takes 10 seconds and catches almost every error. 15. Time for the practice quiz. There are 10 questions covering everything we learned today. For each question, pause the video and try solving it yourself before moving to the answer slide. Ready? Let us go. Question 1. Solve x squared equals 49. Look at the 4 choices on screen and pick your answer. Pause the video now and work through it. The answer is B. X equals plus or minus 7. Apply the square root property. X equals plus or minus the square root of 49, which is plus or minus 7. Both positive 7 and negative 7 are valid solutions. The trap here is choice A, which only gives x equals 7. That is the dropped plus or minus error we talked about. Always remember, when you take the square root of both sides, you must include both the positive and negative roots. Question 2. Solve x squared minus 5x plus 6 equals 0. 4 choices on screen. Pause and work through it. The answer is A. X equals 2 or x equals 3. Factor the left side. X minus 2 times x minus 3 equals 0. Set each factor to 0. X minus 2 equals 0 gives x equals 2. X minus 3 equals 0 gives x equals 3. The trap is choice B, x equals negative 2 or negative 3. That is the sign flip error. When you see x minus 2 equals 0, solve for x by adding 2, not by copying the negative sign. Question 3. Which of the following is the correct quadratic formula? Take a look at the 4 options and choose the right one. Pause now. The correct answer is the one showing x equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. The key things to check: negative b in the numerator, b squared in the discriminant, not 2b, 4ac subtracted, not added, and the entire numerator divided by 2a, not just the square root portion. Memorizing this formula accurately is essential because a single sign error changes the entire answer. Question 4. Solve x squared plus 4x plus 1 equals 0. Give your answer in exact form. This is a free response question, so pause and work through it on paper. The solution is x equals negative 2 plus or minus the square root of 3. You can get there by completing the square or by using the quadratic formula. Let us use completing the square. Move the 1 to the right. X squared plus 4x equals negative 1. Half of 4 is 2, and 2 squared is 4. Add 4 to both sides. X squared plus 4x plus 4 equals 3. Factor. X plus 2 all squared equals 3. Take the square root. X plus 2 equals plus or minus root 3. So x equals negative 2 plus or minus root 3. Leave it in exact form. Do not approximate with decimals. A tip: whenever the problem says exact form, that means keep the radicals. Do not reach for a calculator. Question 5. Solve 2x squared plus 7x minus 4 equals 0 by factoring. Pause and try to find the factors. The factored form is 2x minus 1 times x plus 4 equals 0. Setting each factor to 0, 2x minus 1 equals 0 gives x equals 1/2. X plus 4 equals 0 gives x equals negative 4. When factoring a quadratic with a leading coefficient other than 1, look for a pair of numbers that multiply to give a times c and add to give b. Here, a times c equals negative 8 and b equals 7. The pair is 8 and negative 1 because 8 plus negative 1 equals 7 and 8 times negative 1 equals negative 8. A common mistake is forgetting to account for the leading coefficient. With a equals 2, you must split the middle term and factor by grouping, or check your factors carefully. Question 6. Solve x squared plus 4 equals 0 over the real numbers. Look at the choices and pick your answer. Pause now. The answer is no real solutions. The discriminant is b squared minus 4ac, which equals 0 minus 16, which is negative 16. A negative discriminant means there are no real roots. If we extend to complex numbers, the solutions would be x equals plus or minus 2i, but the question specifically asked about real numbers. This connects back to our discriminant discussion. Always check the sign of the discriminant first to know what kind of roots to expect. Question 7. When is the quadratic formula the best method to use? Look at the 4 choices on screen. Pause and think about it. The best answer is that the quadratic formula is ideal when the equation does not factor easily, or when you are unsure which method to use. It is the universal fallback. The square root property is faster when the equation is already in the form x squared equals k. Factoring is quicker when you can spot integer factors. Completing the square is cleanest when the leading coefficient is 1 and the middle term is even. But when none of those shortcuts apply, or when you just want a reliable method that always works, the quadratic formula is your go-to tool. Question 8. If the discriminant equals 25, what can you say about the roots? Look at the choices and pick your answer. Pause now. Since the discriminant is 25, which is positive, we know there are 2 distinct real roots. Even better, 25 is a perfect square. The square root of 25 is 5, which is a whole number. That means when you plug into the formula, the plus or minus 5 in the numerator will produce rational roots, not irrational ones. So we get 2 distinct, real, rational roots. The discriminant tells us a lot before we even finish solving. Question 9. Solve the equation x minus 3 all squared equals 16. This is a free response question. Pause and solve it on paper. Take the square root of both sides. X minus 3 equals plus or minus 4. That gives 2 equations. X minus 3 equals 4, so x equals 7, and x minus 3 equals negative 4, so x equals negative 1. The 2 solutions are x equals 7 and x equals negative 1. This is the square root property at work. The equation was already in perfect square form, so there was no need for factoring or the quadratic formula. The common mistake is forgetting the negative branch and only writing x equals 7. Question 10. This is a reflection question. In machine learning, what does it mean for gradient descent when a loss function has multiple minima? Take a moment to think about this and formulate your answer. Pause the video. When a loss function has multiple minima, gradient descent can converge to different solutions depending on where you start. The algorithm follows the steepest downhill path from its initial position, so it settles into whichever valley it rolls into first. That local minimum might not be the global minimum. meaning there could be a better solution elsewhere that the optimizer never finds. This is why practitioners use techniques like random restarts, learning rate schedules, and momentum to help escape shallow local minima. In practice, for deep neural networks, many local minima turn out to be nearly as good as the global minimum, which is why gradient descent still works well despite the theoretical challenge. Let us recap everything we covered today. 4 methods for solving quadratic equations. The square root property for equations already in x squared equals k form. Factoring with the zero product property for equations that factor neatly. Completing the square, which is the foundation for the quadratic formula, and the quadratic formula itself, which works universally. We also covered 3 key traps to watch for: the dropped plus or minus error, sign flip mistakes when factoring, and confusing b squared with 2b in the formula. All of these methods connect forward to polynomial equations and optimization in machine learning. Next week is Lesson 12, Rational Expressions. We will learn how to simplify, multiply, and divide rational expressions, which are fractions with polynomials in the numerator and denominator. The quadratic skills you built today will be essential for factoring those polynomials. See you then. Thank you for watching Lesson 11, Solving Quadratic Equations. If this helped, hit subscribe and leave a comment with which method you found most useful. See you in the next one.